Okay, so with this video, what we're going to look at is we're going to look at component forces. So let's take the situation where if we have, let's say we have a guy, and our guy here, he takes a ball and he throws it, and the direction that it moves, the motion that it moves, is in an arc. Okay, so if we look at this motion that this guy has, then we're going to be able to identify a couple of things. First of all, we could say for a fact that we know he didn't throw the ball straight up, because if he threw the ball straight up, the ball would just go up and then come straight back down. We could also say for a fact that the ball didn't, or that the ball was not thrown directly to the right. So what this tells us is that it wasn't straight up, yet it wasn't straight to the right, but rather a combination of both. And when we look at forces, we actually can look and see that whenever we have a situation where an object isn't pushed directly up, directly down, directly right, or directly left, that it's some sort of combination of these. And we can actually figure all these out. So let's clear that. So let's go ahead and let's start here by looking at that exact situation. So if we're looking at a situation where we have a ball, we have a ball, and that ball is thrown in a motion where it arcs, we would be able to say that it was thrown with a diagonal way. So if we were to draw a force diagram, let's go ahead and let's draw our force diagram here. So we have our center point, and we know that it was pushed up in that direction. So with that amount of with a unknown amount of force, okay, and we can say this is force applied. Okay. We also know that once the ball is released, and even before it was released, that it'll also be experiencing the force of weight or the force of gravity. So we have the force of gravity, or more technically correct, the force of weight. Okay? And now these aren't exactly drawn to scale, but for the sake of this argument, or for this demonstration, this is good enough. So we have this force diagram. Now the question is, does this balance out? Well, we know it doesn't, because it accelerates this way and then it starts to accelerate back down once the force is released, but we're not looking at that point. So we're looking at just going up. So is this balanced? Well, there's no forward force, or not forward, upwards force here, and there's no forward force here. All we have is this diagonal. So what we need to find out is, how is this controlling the motion? So if we actually take this and we look at it, let's go ahead and let's not look at the gravity. Let's just look at this upwards force here. So let's look just at that new force here, and let's pick on that. So we're going to ignore gravity, and we're going to draw out that force. So this was our force, applied. Okay? And let's say it was applied, let's say about 50 newtons was applied to that ball to make it fly in that direction. Well, if we take this and we actually look at it, what we could say is there's actually a little bit of up and a little bit of sideways in that force. So if you actually look at it, there's this up component of the force, as well as a sideways component of the force. Because it didn't just go straight up, there's the left and right that made it go left and right, but then again, it didn't just go left and right, there's the up that made it go up. So it's kind of a combination of the two, but it took both of these to make this line. And if you look at this, it makes a very, very obvious thing. It makes a right triangle. Okay? So knowing that, we actually can get a lot of information from this scenario. If I wanted to know exactly how much force, for balancing purposes, how much left and right, because we know that an upwards force has no effect on a rightwards force, and we know that a rightwards force has no effect on a downwards force. So we have to figure out what's left and what's right and all that. How can we figure this out? Well, since this is a right triangle, it takes us all the way back to Pythagoras. Oops, spelled that wrong. Let's fix that. So we have the Pythagorean formula, which is a squared plus b squared equals c squared. Okay, so we have that formula. Well, this works if we've got legs, but let's go ahead and or not legs, if we've got this identified. So let's go ahead and let's identify our legs and our hypotenuse. Well, we know that C is always going to be our hypotenuse. So let's go ahead and let's just put that over here right now. But wait a minute. If you look, we already have that labeled. Well, why would we want to label this over here when we already have it labeled? Could we just replace that? What you'll find out is that'll actually work, and it'll work better with physics. So let's go ahead and let's leave that alone. Let's say that instead of C that we have that equals the force applied. Okay? Well, what about these two legs? Well, that would obviously be A and B. Now, in physics, if we look at this, A is used for acceleration, and B we don't really see, so these aren't exactly great letters to use. So how can we actually replace that? Well, there's a simple thing. Since this is a force diagram, these whole arrows, we're talking about forces in general. So we can actually get rid of those letters, and we can actually replace it with force. So if we replace it with force, it makes a lot more sense. Except one other thing. If we look at it in the terms of mathematics, right now this is saying that this force is equal to that force. Well, that's not necessarily true. So we have to find some way of differentiating it. And for that, we need to go back and we need to look at our axes. So if you take a standard graphing axis, if you look, these fit in very well with a standard axis. You have up and down here. Well, we have up and down here, so that's going to make this the y-axis. So that means this letter, instead of just being F, we can turn it into F of y. And this one's going left and right, this is going left and right, so that's going to make this real simple. That's going to make that F of x. And what we know is that whenever we're dealing with the F of x, or whatever replace this is, because this the same exact concept is used in other things as well. But if we have the F of x, we know that we're talking about the left and right force when it comes to balancing it up. And then we know that if we're talking about the F and y, we're talking about the up and down force. I think I said x and y on the previous one. My mistake. I meant left and right. So we have the F of x is the left and right, and the F of y is the up and down only. Okay? So knowing that, let's go ahead and move this over here. So knowing that, we actually can take this and we can work with it. So let's move this up here. So here we have our situation. Okay, here we have what's going on. So I want to know how much this is this vertical force is applied and how much this horizontal force is applied to create this motion, to create this force. And that's where we're going to go back to an old goodie in geometry. We're going to go back to probably one of the most used mnemonic devices in geometry, and we're going to use SOHCAHTOA. That right there, that mnemonic device is extremely helpful in this situation because it tells us the relationship. And if we take those and we elaborate on them, we know that SO stands for sine of theta is equal to the opposite leg over the hypotenuse. Now, there's a couple of things here. First of all, what is theta? Well, this right here, this theta, it's just basically an abbreviation for an angle. Now, it's not this angle. You can't use that angle. You cannot use the 90 degrees. Frankly, because you need this hypotenuse for any of these formulas to work. What you have to deal with is you have to deal with one of these two angles. So let's just, for the sake of argument, let's pick a different color here. Let's go with green. Let's say that this angle right here, let's call that angle theta. Okay? And let's, for the sake of argument of this one, let's assign theta as 55 degrees. So we have 55 degrees, that's our theta. Okay? So going back to this equation, we have the sine of 55 degrees is equal to the opposite leg over the hypotenuse. Now, what do I mean by the opposite leg? Well, here's the angle. There's the opposite leg. So it's the one that's directly opposite of the triangle for it. If we so in this case, it'll be f of y over the hypotenuse. And we'll solve for this in a minute, which the hypotenuse is obviously 50n. So let's fill that in. So we'll erase that. So that'll be 50 newtons. And if we wanted to do any of the other ones, so we know that SO is opposite over hypotenuse. Ca is cosine of theta is equal to adjacent over hypotenuse. So in this situation, we'd still take, it'd be the cosine of this 55 degrees. And instead of f of y, it'd be f of x up here. And then the hypotenuse would still be the same. And then we'll come to this one in a second. So that's those two. Let's go ahead and let's solve for this one. So let's bring up our calculator. So we have the sine of 55. So we're going to go ahead and hit 55 sine. Now, if you're using a graphing calculator, you don't have to do it in that manner. You actually can just enter in, you can hit sine 55 and blah, blah, blah. But a standard scientific calculator, you need to enter the number first and then hit sine. Okay? And then we're going to multiply it by 50. And we get 40.95, or just rounded that to 1, so it would be 41.0. So let's go ahead and we'll say 41.0 newtons. So that means that our vertical force applied to this, so our F of y, is equal to 41 newtons. Okay? Let's draw that a little bit clearer. 41 newtons. So now that we have 41 newtons here, now we can actually figure out our F of x, because, and we have a few ways of doing that. We can go back to the old a squared plus b squared equals c squared. We can go back to that formula. We can use cosine and go through replacing the hypotenuse with 50 newtons and obviously the theta with 55. Or we can take this and we can go to this last one, the TOA, and that's the one I want to use, so you can see that one. And we'll call this one tangent of 55 equals the opposite leg over the adjacent leg. Now the adjacent leg we know is the f of x, so let's go ahead and let's erase these out. And we know that the opposite is the f of y, which we solved right here. So let's erase opposite, let's erase adjacent, and actually fill in what it's supposed to be. So we know this is f of x, and then we know that this Let's use a different color. We know that this should go right there. And we're going to call this 41 newtons. I don't know what that was. That was a pathetic attempt at an N there. 41 newtons. Now, algebraically, I know that I can switch these out, but let's go ahead and let's do it just for the sake of argument. So I want to get f of x by itself. So to do that, I'm going to go ahead and I'm going to multiply by f of x, multiply by f of x. Okay, so I have fx times tangent of 55 is equal to 41 newtons. I divide the whole thing by the tangent of 55, and I get fx is equal to 41 newtons divided by tangent of 55. Like I said, where those two would just switch. So let's bring out the calculator again. And let's go ahead and let's clear this. So we take 41 divided by, now because I have to use the tangent here, I need to use some parentheses on a scientific calculator. So I'll start my parentheses. I'll hit 55, then I'll hit my tangent button. As you can see, it's right there. Close my parentheses, and I'm going to go ahead and I'm going to hit enter. And that's going to give me 28.7. So coming back to here, we've got that equals, say 28.7. Yeah, so we've got 28.7 newtons. So there's my f of x. So what I've done is I've calculated the vertical, the y component, and the horizontal, or the x component, for this entire thing. Now, like I said, as you see, you can once you have two of these things, you can figure out any of this, and then what you can use there is you can go back to this scenario, and now we can figure out why this is actually balanced out, because if we know that going down we have our vertical component, we know that it's going up with 41 newtons. We know that the gravity or the weight has to be less than that, otherwise it wouldn't go up at all, because gravity would have won, it wouldn't have beat that. We know it also can't be balanced, because if it did, it wouldn't have accelerated up at all, and we know it can't be greater down, because then it would have accelerated down. So hopefully this will help you out. If you have any other questions or any other clarifications, or you notice any errors, please feel free to leave a comment in the comment section. And if you have any requests for any videos specifically, please feel free to let me know. Thank you for watching.